Welcome back to the deep dive. Today, we're on a mission to short-circuit your learning curve for what is, I think, the most critical part of the C++ standard template library, the vector container.
Absolutely.
If you've ever worked in C or even older C++i, you know the pain point we're talking about. You're wrestling with static C arrays, manual memory allocation.
All that malloc and realloc mess.
Exactly. It's a headache.
Yeah.
So our goal today isn't just to explain what a vector is, but to give you the insights and the best practices that really make it an indispensable tool.
It's a complete game changer. You can think of it as the ultimate advanced dynamic replacement for that traditional C array. It's really the backbone of the whole STL container library, appear to powerful things like map, set, and queue.
Right. So if you need a sequence of data that has to grow or shrink, this is where you start.
This is where every modern C++ developer starts.
So our deep dive is simple. We're going to unpack its mechanisms, its built-in efficiencies, and the key functions that will save you, potentially thousands of lines of code. And let's get one rule on the table right away. To use std.vector.
You have to include the vector header. No exceptions.
No exceptions. Okay, let's start with the absolute basics. What is it? At its core, a vector is a sequential collection of values. You get to them with a numeric index, starts at 0. So, from that basic access perspective, it feels just like a C array.
And that familiarity is completely intentional. But the differences are where all the power comes from. Unlike a C array, a vector is a templated type.
A templated type.
Right. It's designed to be totally flexible about what kind of data it stores. Think of it like a reusable mold, kind of like a template struct type you might write yourself.
Yeah.
The T in the template just stands for whatever type you want to plug in.
And that templating is really the key to its universal appeal, isn't it?
It is. But it also comes with a critical instruction.
Mm-hmm.
Because it's templated, when you declare or create that vector object, you must specify the type of element you're going to store.
So you can't just say vector minus.
No, you have to be specific. Vector in my integers. Or say vector std.string my names.
Mm-hmm.
You're telling the compiler what you're storing so it knows how much memory to plan for.
It really reminds me of learning the C++ string container. That was sort of our first advanced container.
Also in the ST namespace.
Right. But the vector just blows that away because a string can only store characters. A vector can store, anything. Integers, floats, complex objects, even other vectors.
It's universally applicable for sequential data.
Okay, let's move on to the real magic of the vector, which is capacity management. If you have a C background, you know that resizing an array means what you call malloc or realloc, and then you have to copy everything over.
It's slow, it's error-prone, a total nightmare. The vector just handles all of this automatically.
So this is where we need to introduce a really vital distinction for you.
The difference between size and capacity.
Right.
The size function tells you how many elements are currently in the vector. It's the logical length of your data. Capacity, on the other hand, tells you how much memory is actually allocated, or the number of elements it could hold before it has to go ask the operating system for more space.
So capacity is the size of the cup, and size is how much water is actually in the cup.
That's a perfect analogy.
Yeah.
And this leads us straight to the vector's most critical performance optimization, geometric capacity growth.
Okay.
When you use pushback to add an element and the vector hits its capacity limit, it doesn't just ask for one more space. It typically allocates a huge new block of memory, often doubling its current capacity, and then it copies all the old elements over.
Hang on, if it's copying all the elements every time it grows, doesn't that make pushback really slow? I thought this thing was supposed to be efficient.
That is an excellent critical question. It seems slow because, yes, occasionally when you hit capacity, that copy is an expensive ON operation, but, and this is the key, because the capacity doubles, these expensive reallocations happen less and less often as the vector grows. So over a large number of insertions, the average time complexity of pushback is what we call amortized O1.
So it's effectively constant time.
It's effectively constant time. And understanding that trade-off is really what separates a professional programmer from a novice.
That is the real aha moment. So capacity management isn't just about convenience, it's a high-performance feature.
It absolutely is. And this management is built right in. We have size and capacity, but also empty, which just checks if the size is 0. And for optimization, we have reserve n. If you know you're going to store, say, 10,000 items, you can call reserve 10,000 right at the start.
And that prevents all those little reallocations along the way.
Exactly. No costly copying.
And beyond that, The modification methods just simplify everything that was so painful with C arrays. To add an element before, you had to redefine the whole array.
Now you just call a member function.
Yeah.
Clear. Wipes the vector. Clean resets the size to 0, but often keeps the capacity. And then there's pushback element, which adds an item to the end, and its opposite, popback, which removes the last one. These make dynamic resizing just trivial.
Okay, so we've covered putting data in. How do we get it out? You mentioned there are 4 specific ways with different trade-offs.
Right. 4 dedicated access methods. The first 2 are for index access. You have @index, which is the safer method.
Safer how?
If you try to access an index that doesn't exist, say index 10 in a vector of size 5, we'll throw an exception. It protects your program from crashing.
Okay.
The second way is the standard array syntax, the operator index. This is often a bit faster because it skips that bounds checking.
Ah, so it's a speed versus safety trade-off.
It is. If you are 100% certain your index is valid, it's quicker. But if you're wrong, you're likely looking at a crash or undefined behavior.
So if I'm writing robust code, I probably use @, but in a tight performance critical loop where I know the index is good, I'd use the square brackets.
That's the professional choice, yes. Then you have 2 little utility methods. Front, a quick way to get the first element, and back, which gets you the last element. And what's really cool is that if you've already learned the C++ string container, these names operator, front, back are identical. Shows the consistent design of the STL.
That continuity is great. Now let's talk about traversal. We can use a simple index loop, but you mentioned something more advanced, iterators.
Iterators are, well, they're more than just fancy pointers. They are the glue that holds the entire standard template library together. They allow you to move through the container, but more importantly, they make the vector compatible with the entire library of generic C++ algorithms like std.sort or std.find.
Which means you can write an algorithm once and it works on a vector, a list, a set.
As long as it uses iterators, yes. It makes your code incredibly portable and robust. It's a huge time saver.
So what are the key iterator functions we need to know?
There are 4 primary ones. You have begin, which returns an iterator that points directly to the first element. And then you have end. Now, this is where you have to be very clear. End does not point to the last element. It points to the position just past the last element.
Oh, right, the fence post analogy. If you have 5 items, begin is the first one, and end is like the post standing just after the 5th one.
A perfect analogy. It signals the end of the sequence. If you try to actually access the data at end, you get undefined behavior.
Got it.
For reverse traversal, you just flip the roles. Our begin points to the last element, and ren points to the position before the first element. Understanding those boundaries is absolutely essential.
So connecting this all back to, bigger system design, how do vectors perform when you pass them between functions?
This is where so many programmers accidentally create huge performance bottlenecks. The rule of thumb for any container type that holds a lot of data is you must pass it by reference.
And that goes back to that copying cost we talked about, right?
Exactly. When you pass a vector by value, you create an entirely new copy of it. Every single element gets duplicated. If your vector holds 1 million user records, that copy operation will just kill your performance.
And that's true for returning vectors from functions, too. You can return a copy, but it's expensive.
It is.
That makes sense, but then, wait. If the language designers worked so hard to manage memory for us with geometric growth, why didn't they just implement a smarter default? Say, using move semantics automatically when returning a vector to prevent that massive copy?
That is a fantastic question. And modern C++ does often optimize that away with something called return value optimization or move semantics. But the underlying cost of value semantics is still there. The design philosophy really emphasizes explicit control. So the absolute best practice, if you want zero-copy performance when getting results out of a function, is to pass the vector as a non-constant reference into the function.
So the function fills up the vector you gave it instead of creating a new one.
Exactly. It modifies it in place, no data copying on return.
Okay. What about other operations on the whole vector at once?
Right. So for convenience, the vector overloads the assignment operator and comparison operators like EAFE. This means you can just assign one vector to another or compare them, and it handles the element-by-element work for you. But this only works if the type you're storing has a defined ordering.
So with a vectorant, I can just say if vector A equals vector B. But if I have a vector of my own custom objects and I haven't told the compiler how to compare them,
then the vector comparison will fail.
correct.
Now here's the key exception, and it connects to our final question for you. The standard input-output operators the stream operators in SPI, do not work on vector objects as a whole. You can't just write std.countMyVector.
Oh, that's a huge exception. You have to loop through it yourself.
You have to iterate, and that points to a very specific design choice.
We'll come back to that. Before we do, what about complex structures? A two-dimensional vector.
It sounds intimidating, but it's really simple. It's just a vector where the elements you're inserting are themselves vectors. You declare it as vector-vectorant.
And it basically acts like a 2D array, but it's dynamic.
Dynamic in both dimensions.
Exactly. Okay, let's switch gears to application. In the real world, you're going to be sorting vectors constantly. The source material is very clear on this. Use std.sort from the algorithm library. Don't write your own. Why is that rule so important?
Performance and stability. The STL sort function uses highly optimized hybrid algorithms like introsort. It's a mix of quicksort, heap sort, and insertion sort. It guarantees you O(n) log n time complexity. If you're dealing with a big data set and you try to write your own bubble sort, well, it's just not competitive. And it's probably buggy.
Just the library.
Always trust the library.
So to really get a handle on this, you need to apply it. You mentioned an airline reservation system exercise. How would a vector structure something like that?
Right, so you have 10 rows, 2 seats each. You have to track availability, sales.
My first thought would be a vector-vector bool. The inner vector has 2 booleans for the 2 seats. True if it's taken.
That's a valid starting point, using a 2D vector of primitive types. But once you need to track prices and passenger names and generate reports, that structure falls apart.
It gets messy.
Very messy. A much better, more object-oriented design is a vector of structs, maybe a vector row struct. Each row struct would then hold details for that row, including maybe 2 seat struct objects, which would hold the price, status, passenger info.
I see. So you're moving from just storing data to using the vector to hold a complex domain model. That's what real-world systems do.
That's where the real learning happens, yes.
We also see exercises like splitting a string into a vector of words. That forces you to really grapple with traversal and pushback.
It does. And for anyone into competitive programming, the Kattis problems mentioned are spot on. Pay special attention to problems that require sorting on 2 different keys, like the roll call problem.
How does that work?
It forces you to customize std.sort using a custom comparison function or a lambda expression. It's a true test of your mastery of iterators and algorithms. So to wrap this all up, the C++ vector is the advanced template successor to the C array. Its power comes from that geometric capacity growth, which gives pushback amortized O(n) performance. Remember, you have to specify the element type, and please avoid passing large vectors by value.
Right. So we've covered its speed, its structure, its essential functions, but we keep circling back to that one peculiar design choice. The assignment and comparison operators work on the whole vector object right out of the box, but the standard I/O stream operators do not. Why? Why are vectors designed to be so easily copied and compared as a single unit, yet they resist being streamed to standard output or input? What does that tell you about the vector's primary purpose? Is it meant to be a fundamental internal component that talks to other parts of your system, rather than a format for raw, immediate user interaction? It's a question of internal utility versus external representation. We encourage you to dive into the linked STL notebooks to explore that design intent. Thanks for joining us for the deep dive.